Welcome to our comprehensive guide on cryptography, interview questions focused on data protection and security fundamentals. Cryptography forms the backbone of modern digital security, protecting sensitive information from unauthorized access. Today's discussion covers 4 essential areas that frequently appear in technical interviews. First, encryption algorithms, which include both symmetric and asymmetric encryption methods used to secure data transmission and storage. Second, digital signatures that provide authentication and non-repudiation capabilities. These topics represent the core concepts that every security professional must understand to build robust, secure systems in today's digital landscape. Encryption algorithms fall into 2 main categories: symmetric and asymmetric encryption. Symmetric encryption uses a single shared key for both encryption and decryption processes. The most widely used symmetric algorithm is a ES, or Advanced Encryption Standard, which provides strong security for bulk data encryption. Other important symmetric algorithms include DES and triple DES, though these are considered legacy due to security vulnerabilities. Blowfish and Twofish offer alternative symmetric options, while Cha-Cha-20 represents modern stream cipher technology. Asymmetric encryption, on the other hand, uses a pair of mathematically related keys. RSA, named after Rivest, Shamir, and Adelman, remains the most popular asymmetric algorithm. Elliptic curve cryptography, or ECC, provides equivalent security with smaller key sizes, making it efficient for mobile devices and embedded systems. Advanced Encryption Standard, or AES, is the gold standard for symmetric encryption. The Python implementation demonstrates the practical application of AES using the Fernet library from the cryptography package. The process begins with generating a cryptographically secure key using fernet.generate_key method. This key serves as both the encryption and decryption key, which is the defining characteristic of symmetric encryption. To encrypt data, the plaintext message is first encoded into bytes, then passed through the cipher.encrypt method. The resulting encrypted data appears as seemingly random bytes, completely unreadable without the proper key. Decryption reverses this process. The encrypted data is passed through cipher.decrypt, then decoded back to readable text. AES provides strong security guarantees when implemented correctly, making it suitable for protecting sensitive information in production systems. Understanding the fundamental differences between symmetric and asymmetric encryption is crucial for any cryptography interview. Symmetric encryption uses the same key for both encryption and decryption operations. This shared key approach offers excellent performance characteristics, making it ideal for encrypting large amounts of data quickly. However, symmetric encryption faces the key distribution challenge. How do 2 parties securely share the secret key without it being intercepted? Asymmetric encryption solves this problem by using a key pair consisting of a public key and a private key. The public key can be freely distributed, while the private key remains secret. This approach enables secure communication without prior key exchange, but comes with significantly slower performance compared to symmetric methods. In practice, modern systems often combine both approaches: asymmetric encryption for secure key exchange, followed by symmetric encryption for actual data protection. Digital signatures provide 3 critical security services that are essential in modern cryptographic systems. Authentication verifies the identity of the message sender, ensuring that the communication comes from the claimed source. Integrity guarantees that the message content has not been altered during transmission, detecting any unauthorized modifications. Non-repudiation prevents the sender from denying that they sent the message, providing legal accountability in digital communications. Additionally, digital signatures often carry legal validity in many jurisdictions, making them equivalent to handwritten signatures for electronic documents and contracts. These properties make digital signatures indispensable for secure email communication, software distribution, financial transactions, and legal document processing. The combination of these security services creates a comprehensive solution for establishing trust in digital communications. The RS, a digital signature implementation, demonstrates the practical application of asymmetric cryptography for authentication. The process begins with generating an RS, a key pair, using a public exponent of 65,537 and a key size of 2,048 bits. These parameters represent industry-standard values that provide strong security. The private key creates the digital signature using the sign method, which takes the message, a padding scheme like PSS, and a hash function such as SH256. The padding scheme adds randomness and prevents certain types of attacks, while the hash function creates a fixed-size digest of the message content. The resulting signature can only be created by someone possessing the private key, but anyone can verify it using the corresponding public key. This asymmetric property enables secure authentication without revealing sensitive key material. Key management encompasses the complete lifecycle of cryptographic keys, from creation to destruction. Effective key management is often considered the most challenging aspect of implementing cryptographic systems, as poor key handling can compromise even the strongest encryption algorithms. Key generation requires cryptographically secure random number generators to ensure that keys cannot be predicted or reproduced by attackers. Key storage involves protecting keys during their active use, typically using hardware security modules, or HSMS, which provide tamper-resistant hardware protection. Key rotation involves regularly updating keys and managing the transition from old to new keys without disrupting system operations. Finally, key destruction ensures that expired or compromised keys are securely deleted from all systems, preventing future unauthorized access. Organizations must establish comprehensive key management policies that address each of these phases to maintain strong security posture. The key lifecycle consists of 4 distinct phases that ensure cryptographic keys remain secure throughout their operational lifetime. Phase 1, generation, involves creating cryptographically secure keys using hardware random generators or cryptographically secure pseudorandom number generators, known as CSPRNGS. The quality of randomness directly impacts the security of the entire cryptographic system. Phase 2, distribution, focuses on securely sharing keys with authorized parties through key exchange protocols and secure communication channels. This phase often represents the weakest link in many cryptographic implementations. Phase 3, storage, protects keys during their active use through hardware security modules, encrypted databases, or secure enclaves that provide isolation from other system components. Phase 4, destruction, involves safely deleting keys when they are no longer needed using cryptographic erasure techniques and secure deletion methods that prevent key recovery from storage media. Understanding common security vulnerabilities helps identify potential weaknesses in cryptographic implementations. Weak encryption represents a significant threat when organizations use outdated or compromised algorithms such as DES, MD5, or RSA keys with insufficient bit length. These legacy algorithms may have been secure in the past, but are now vulnerable to modern computational attacks. Poor key management practices create vulnerabilities through insecure key storage, weak passwords, hard-coded keys in source code, or unencrypted key storage. Implementation flaws occur when developers make coding errors in cryptographic functions, leading to side-channel attacks or timing vulnerabilities that can leak sensitive information. Social engineering attacks target the human element, using techniques like phishing, credential theft, or insider threats to bypass technical security controls entirely. These human factor attacks often prove more effective than direct cryptographic attacks. Mastering cryptography interview questions requires understanding several key areas. Algorithm knowledge forms the foundation. Clearly distinguish between symmetric and asymmetric encryption, understanding when to use each approach and their respective advantages and limitations. Digital signatures require comprehension of authentication, integrity, and non-repudiation concepts, along with practical knowledge of how these properties secure digital communications. Key management expertise involves understanding the complete key lifecycle process, from secure generation through proper destruction, recognizing that poor key management can undermine even the strongest cryptographic algorithms. Security awareness encompasses recognizing common threats and implementing best practices to mitigate risks. Success in cryptography interviews depends on combining theoretical knowledge with practical understanding of real-world implementation challenges. These fundamentals provide the foundation for building secure systems and advancing in cybersecurity careers.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.